My name is Kostya Serebryany, and I represent here a team of engineers from Google Moscow. We develop and deploy various testing tools, and this is what I will be speaking about today. I will quickly remind you about ThreadSanitizer, our first LLVM-based bug detection tool, which was presented here last year. This tool detects such bugs as use after free and buffer overflows in C++ programs. Then I will move to two new tools. One is called ThreadSanitizer, and it detects data races in C++ and Go programs. And the third tool is called MemorySanitizer, and it detects uninitialized memory reads, also in C++. All the three tools are similar, but they find different classes of bugs. So a quick summary of ThreadSanitizer from last year. It finds more or less all kinds of memory corruption bugs known in C++, such as buffer overflows in stack, heap, and global variables, uses of freed memory, double free, incorrect use of memcopy, and many other memory corruption bugs. It consists of two parts. One part is an LLVM compiler model, which is quite compact. It is about 1,000 lines of code. This LLVM model instruments all loads and stores in the program, and also inserts what we call red zones around stack and global variables. The second part of the tool is the Runtime Library. It's a bit bigger, and it is essentially a specialized malloc implementation, plus a little bit of bookkeeping to produce error messages. This is an example of a test case and a bug report from ThreadSanitizer. As you can see, you have allocated some heap memory, then you have deleted it, and then you continue using it. So if you compile this test with Clang and with a special flag, and then run the application, you will get a full information about the bug. You will see where the faulty access happens. You will see where the memory has been deleted previously, and you will even see where it has been allocated before that. The tool uses what is called shadow memory. Shadow memory is a part of address space which keeps metadata for the application memory. For ThreadSanitizer, it is very simple. We take 1/8 of the address space, and we say that this part of address space belongs to the tool. And when we want to get metadata associated with a particular address of your application, we just divide it by 8. So this gives us an address of metadata byte. And if this byte is not 0, we report an error. This is our marketing slide. The tool is very fast. We typically see less than 2 times slowdown compared to fully optimized binary. Compare that to Valgrind, which is typically at least 20 times slower. The memory overhead of the tool is reasonable, and these properties of the tool allowed us and our users to find enormous amount of bugs more or less everywhere. One of our first targets was Chrome, and the Chrome developers and security researchers found more than 500 security bugs in Chrome, and some more bugs were found by external users. Today, instrumented Chrome runs on 2,000 machines 24/7. Our users in open source community found more than 1,000 bugs everywhere else: Firefox, FreeType, FFmpeg, and even a dozen bugs in LLVM itself. This is my slide for hardware developers and vendors. As far as I understand, most of the key players are here, at least presented somehow. We believe that simple hardware support can speed up the tool from 2 times slowdown to 20% slowdown. If you have any comments about it, please find me at the poster session later today. Okay, moving to moving to the two new tools. And the first one will be a data race detector, TSAN. So 4 years ago, my team developed a tool which was called ThreadSanitizer at that point. It was a race detector based on Valgrind, and we have used it since then. It is, and it was, and it is insanely slow. It is usually slower than Valgrind. Still, it found a few thousand bugs for us, many critical bugs, and it is still faster than most of other tools on the market. If you're interested in the old algorithm, we have a paper published in 2009. But the speed and the usability of the old tool was really not perfect. So last year, we decided to completely re-implement this thing. And based on our success with ThreadSanitizer, we decided that LLVM is the best place to do it. So the second version of ThreadSanitizer, which I present now, uses a very simple compile time instrumentation. It's about 400 lines of LLVM code. And the fully redesigned Runtime Library, which actually contains all the logic. It is fully parallel. It doesn't have any expensive synchronization on the fast path. And it scales to huge applications that have at least dozens of threads. And it has predictable memory footprint. So this is how it works from a user perspective. Again, you have a C or C++ program. You compile it with Clang with a special switch, and you run the application. In this program, you can see that we have a data race on a global variable. One thread writes to a global variable something, and without any synchronization, another thread does the same. So if you run this program, instrumented, you will see the first access, you will see the previous access to the same memory, and you will also see some extra information. In this case, you will see where the thread was created. As I mentioned, the compiler instrumentation is very simple. More or less, we prepend every memory access with a function call. So if the original program contained some store or load or anything, we add a function call before that. We also add one function call at the function entry and one at the function exit. This tool also uses shadow memory, and it is also directly mapped. Currently, the tool works only for 64-bit Linux, and this is how mapping looks like on that system. The higher portion of address space is dedicated to the application. So this is where your heap, stack, and BSS is stored. Then there are two sections in the middle and at the bottom that are unprotected. No one can use it. And the biggest section in between is dedicated to shadow. So if you want to compute a shadow address from the application address, you simply apply a mask and multiply by 4. So this is very simple arithmetic. What do we store in that shadow memory? In that shadow memory, we store what we call shadow cells. A shadow cell, by our definition, is an 8-byte word which contains 4 pieces of information. First is shadow cell represents one memory access that happened in some past. And about this memory access, we know a few things. First of all, thread ID, which thread accessed the data. Then what is called epoch or scalar clock, when that access happened in the given thread. Then we store 5 bits of position and size of the memory access, and 1 bit which represents whether it was a read or a write. Note that these 64 bits is complete information about one given memory access. you don't need to go to any external tables or any external data to get additional information. The shadow memory maps one 8-byte word of the application at the left on this slide to 4 shadow cells. So this means that the memory overhead, we use additional 4x of memory. And these shadow cells represent 4 memory accesses to these 8 bytes of application memory that happened in the past. Let me show you how we use it on a simple example. Suppose we are touching some particular piece of memory for the first time. We have this our 8-byte word, and we are touching the first 2 bytes. We are writing to it. So after this access, we will have one cell filled with the following information: thread ID 1, epoch some number, position from 0 to 2, and this was a write access. The second memory access to this memory comes from thread 2, and it is a read, and it reads some other bytes. So we just store the information in the second slot. The third access comes from thread 3. It reads the first 4 bytes, and it has also some scalar clock from its thread. So the question now, whether we have a data race. So we have 2 memory accesses, which are marked red on the slide. At least one of them is write. They overlap, and we still need to figure out whether there is a data race. So this is the situation when we need this epoch or scalar clock number. And based on these 2 numbers, we compute what is called happens before relation. And if first access does not happen before the second access, we have a data race. Happens before relation is computed very fast. It is a constant time operation. We basically need to load one word from thread local storage and compare it with the current shadow slot. The idea is very similar to Fast Track, a paper published a few years ago. When all the slots are full, we need to remove one of them. And the best strategy we found so far is just to throw away a random one. This is what we do. We are working with data race detection for almost 5 years now. And our experience with users shows that users really need all the information they can get about the data race to fix it. Because if you just say, hey, you have a data race, the user will reply you, of course we have, but how does it help me? You need to give him everything you could. And the 2 major pieces of such information is the stack traces of the 2 memory accesses that are involved in a race. So when the race is actually detected, you can easily produce the current stack trace. Just unwind the stack and show it. But it is a little bit challenging to show the previous stack trace. Because when the previous access happened, you didn't know that it will be involved in the data race. For the first version of ThreadSanitizer, we were storing a fixed number of frames per every memory access. Default was 10. This information was never lost. And we have had to do reference counting and garbage collection for those frames, and it was a little bit of nightmare. Still worked. In the new tool, we came up with a different approach. We have per thread cyclic buffer of events that happen in this particular thread. Each event is a 64-bit integer, which basically represents 3 bits of type of event, and the rest is the PC where the event happened. Events are memory accesses, reads or writes, and things like function entry, function exit. Since this is a cyclic buffer, the information is lost after some time, but the buffer size is configurable, and we most usually see no problem with this. So when a data erase is actually detected, we use this cyclic buffer to replay the events back to produce an infinite number of stack frames in the report. The runtime library for TSAN has to intercept a large set of functions from libc mainly. First of all, this is also a replacement for malloc. Then we have to know everything about synchronization, like pthread, mutex, lock, etc. And we need to know the most popular functions like memcopy, memcompare, string length, because these functions access memory and they can access memory in a racy way. But since this is libc, we don't instrument it, we don't see it. So we wrap these functions, replace them with our own implementations. The tool also handles atomics, atomic instructions, by replacing an LLVM IR atomic instruction with a function call. On this slide, we have atomic load with acquire semantics. We just replace it with our own library function call. The previous speakers have been telling us about various benchmarks, including SPEC 2006. Unfortunately, SPEC 2006 is not applicable to benchmark ThreadSanitizer because ThreadSanitizer cares about threaded applications. So we have a lot of our own internal benchmarks, and three sort of representative are shown here. First is an RPC benchmark, something that does a lot of computations in a lot of threads. So the old tool had like 40x slowdown, the new tool has like 7x slowdown. And the comparison is Clang 01 versus the tool applied with 01 optimization level. So this is more or less apples to apples. Another test is a load test for our web server. So this is an application that sleeps a lot, waiting for network events and such. The old tool had 25x slowdown. The new tool has very small slowdown, less than three times. And finally, there is a benchmark which handles strings. It doesn't have threads, so we just evaluate how we work on a single threaded performance. The new tool has about six times slowdown. We started deploying the tool very recently, so we don't have as many trophies as ThreadSanitizer has. But still, in our server-side software, which is our primary target now, we found a couple of hundreds data races. Some of them are really scary. As I mentioned, the tool also works for the Go language, and we found about 80 bugs in the Go programs, including some in the standard Go library. Since our server-side applications, some of them use OpenSSL, we also found races in OpenSSL implementation, and one of them was fixed, the other were declared benign, although I'm not sure if races could be benign according to the standard. And we hope that more bugs will come soon because we are starting to deploy the tool on Chrome. One bug found last week. So the key advantages of this new tool over all previous tools is that it is very fast. Typically, it's 10 times faster than the competitors. And it has native support for atomics. So if your program does synchronization other than by pthread, or if you're using pure atomics, it is almost impossible to use things like Helgrint or Intel Parallel Inspector, because these tools use binary translation, and you cannot catch the atomic synchronization using those tools without special tricks. The tool also has some limitations. Today, it works only for 64-bit Linux. It is hard to port the tool to 32-bit platforms, to any 32-bit platform, because the tool likes very much atomic 64-bit loads and stores. The tool also heavily relies on thread local storage, so your platform needs to have it. And finally, the tool, as all our tools, doesn't instrument pre-built libraries like libc. It doesn't handle inline assembly. This is something we want to handle, but we don't do it yet. OK, moving to the last tool, MemorySanitizer, which finds uninitialized memory reads in C++. This is how msan report looks like. We have a test that has array on stack. It is some of the members of the array are not initialized, and we're using this one of the uninitialized member in an if statement. So again, as with the previous tools, you compile the test with Clang with a special switch. You run the application, and the report you get contains two pieces of information. First piece is where the uninitialized data is being used. Of course, this will be a stack trace in the general case. And the second piece of information is where this memory has been allocated. If this is a stack array, it gives you the name of the object on stack and the name of the function. If this was a heap, it will give you a stack trace. So for those who are familiar with Valgrind, this is very similar to what Valgrind provides for uninitialized reads. The difference is that since we're doing it on a compiler level, not on binary level, we can actually show more information. Namely, we can show the name of variable. For those of you who have debugged Valgrind reports, this could be a bit of a problem when Valgrind says, well, somewhere in this frame. Again, the tool uses the shadow memory approach. We have bit-to-bit shadow, where one bit of shadow memory shows whether the corresponding bit of the application is initialized. The memory is marked uninitialized when it is returned by malloc or when local stack objects are created. So at these points, what we call poison the memory, saying that it contains garbage. When we see arithmetic operations on data, we have to propagate the shadow. I will cover it later. And the shadow is unpoisoned when constants are being written to the application memory. This is how the shadow mapping look like for MemorySanitizer. We divided the address space into 4 equal parts. The first one and the third one are unprotected. No one can touch it. The upper part belongs to the application, and the second part belongs to the tool. And the mapping is very simple. You just subtract a constant from the address. A little bit about shadow propagation. So detecting uninitialized memory usage is a little bit tricky, because not every load of uninitialized data constitutes a bug from the point of view of C++ standard. The hardest example from my point of view is given here. So we have a structure that contains 2 fields of different sizes. And due to alignment requirements, we have a gap in this structure, 3 bytes, which are never used by anyone. So if no one uses them, no one will probably care to initialize them. So if you created an object of this type, you will have 3 bytes of garbage, which is perfectly OK. But when you start copying these structures, you are loading this garbage and storing it back. And some of the tools which do things incorrectly with this respect will start reporting bugs at this point, thus making the tool useless. Valgrind doesn't do this. Valgrind reports uninitialized memory reads only when the actual uninitialized data is used in a branch or is passed to a syscall or somehow otherwise affects the behavior of the program. So we need to make sure that we propagate these poisoned bits through the arithmetic. And we're doing very similar things to what Valgrind does. For example, when two values are added together, we take the shadows of those values and OR them together. For some special instructions like bitwise AND, we have to do a little bit more sophisticated things. And this approach is more or less covered in an old Valgrind paper. We're not doing something widely different here. One thing that differentiates us from Valgrind is that we have to shadow function parameters and return values in a different way. Because Valgrind can shadow registers and stack. We cannot, because at the LLVM IR, there are no such things. So we pass the shadow for parameters and return values through thread local storage. One key thing of this tool is how we show the reports which memory has been uninitialized. This is very similar to the recent addition to Valgrind, which is Valgrind flag -- track origins. It is a very useful flag in Valgrind, and we also implemented a similar feature in MSAN. The problem, for example, you have two heap objects. You add them together, and then you pass the result of this addition to some instruction that affects the program behavior. And at this point, the tool says that this thing contains garbage. But the question, where did this garbage came from, whether from A or from B? So Valgrind propagates the origins of uninitialized memory alongside the shadow, and so do we. Each origin, and origin is either a malloc stack trace or a stack frame, is a 4-byte ID number. We use one-to-one mapping for IDs, so 4 bytes of memory have single ID. And this thing introduces additional 2x slowdown on top of the regular slowdown of the tool. This is how we use secondary shadow for the origins. So we just use the third part of the address space to store the origins. And the mapping is, again, very simple. We use one instruction for that. The overhead of MSAN is extremely low compared to Valgrind. Without tracking origins, slowdown is 3 times and memory consumption is 2 times bigger. With tracking origins, everything well, essentially doubles. There is a tricky part. If address sanitizer or thread sanitizer doesn't see some memory access, it will just not report any bug. With memory sanitizer, we don't have this luxury. If we miss a single write to a memory, we may start reporting false positives in random places. So the tool must monitor all stores in the program, including libc, libc++, system calls that write to user memory, etc. We have several solutions or ideas how to handle it. First of all, for some of the applications, we can simply provide instrumented libc++, and we, by the way, use the LLVM libc++ implementation on Linux. It works perfectly. And we wrap a number of important libc functions. So this approach works for a lot of what we call console applications, the things that take input files and produce output files. For example, LLVM is one of such cases. The tool is completely usable for LLVM. We found one bug there. Another approach to fix the problem is to instrument all the libraries which are not instrumented at compile time using some kind of dynamic translation tool. We have a prototype based on DynamoRio. It is a little bit slow, slower than we want it to be, but the combination is still much faster than Valgrind. And two other ideas, this is something we want to implement but didn't yet. First of all, it would be nice to instrument all the libraries statically, but we have no idea if this is possible in general case. Maybe not. And last but not least, I really hope that at some point our industry will come to a situation when we compile everything. Everything meaning everything except for system calls. So libc has to be compiled alongside your program. And it will, by the way, help other tools like LLVM and ThreadSanitizer. We're just starting to deploy MSAN at Google. And our first target was a proprietary application of more than 1 million lines of C++ code. It's a console application which was not tested with Valgrind previously. And in the first run, we found more than 20 unique bugs in the program and spent less than 2 hours to do it. Valgrind finds the same bugs, but spends more than 24 hours on the same machine. And for stack-related reports, MSAN produces much more understandable error messages. As I mentioned, the LLVM bootstrap is fully usable with MSAN. We found one bug in LLVM, and we're ready to set up regular runs. And we're starting to deploy the tool in Chrome. We found a couple of bugs already, and there we have to use the dynamic component with DynamoRio, and it is still 7 times faster than Valgrind. So to summarize, we have 3 dynamic testing tools based on LLVM instrumentation. ThreadSanitizer, which finds memory corruption, I believe it's a must-use for everyone who uses C++. It is supported on a bunch of platforms, and a bunch of other platforms are work in progress. You're welcome to use it. Second tool, ThreadSanitizer, it finds data races. We also believe it's a must-use if you have threading in your programs. It works for C++ and Go, and currently it's only supported on 64-bit Linux. The third tool, MemorySanitizer, finds uses of uninitialized data. It is still work in progress. It's not even committed to LLVM yet under code review. But it is already usable for a large set of console applications. And again, today it works only on 64-bit Linux. I would be happy to take questions, and please use microphone. Thank you.
Ronan Carriel from Silcan. A great talk and great work, thank you. Could you show again the shadow memory approximation with a 1-to-1 bit?
For which tool?
Yeah, I guess you could add some numbering on your slide. Anyway, it was before, I guess. Yes, just the next one. Yeah, I have a question about how you propagate shadow values through the addition, for example. If you consider, for example, you have b equal -1, and in this case, you will have a carry propagation from the lower bit to the upper one. So I guess you will miss a lot of uninitialized memory propagation in this case. Is it correct, or?
I agree this is not a strict science. So we have to balance between false positives and false negatives. We try to not allow false positives. So we may miss some of the cases. We didn't reinvent the wheel here. We basically took the same logic from Valgrind, because we think it is very well tested. But okay, it can have false negatives. It can miss some of the rare bugs.
But maybe could it be possible to add an option to your tool, to add a soundness option? That means that you detect, for example, all the potential error case, even if you add a lot of false positive. Do you think you could add this
Absolutely.
kind of
Such options are easy, and in fact, we have a couple of such options already that balance between speed, accuracy, and false positives, false negatives.
I actually have two questions, but one of them is very quick. So on ThreadSanitizer, when you compared it, ThreadSanitizer V2 with V1, I guess V1 does instrumentation on runtime.
Yes.
And V2 does instrumentation, of course, on compile time.
Yes.
And other tools you compare to them also do instrumentation runtime. So it's not exactly apples to apples comparison.
Well, this is what user sees, right? The technology is different, of course, but the data demonstrates that when we're using compile time instrumentation, this technology is actually better for this kind of tools.
Faster. Well, yeah. So frankly, first question. And second, again, on ThreadSanitizer, how do you deal with false positives that might be present even with perfect tool, because the user might employ his or her own synchronization machinery?
So we had a lot of problems with false positives with the first version of ThreadSanitizer when the user had atomic synchronization. Now, in fact, we do just simply understand the synchronization, whatever it uses pthreads or any custom locking. So I would actually say that we don't have false positives. At least I haven't seen any. We have seen some strange cases when we think that this is a true positive and the user thinks that this is a false positive. And we sometimes have to educate users saying that, hey, folks, volatile in C++ cannot be used as a synchronization, sorry. But other than that, with the second version of the tool, we don't see false positives.
Hi, Kilan Gurka from Cambridge University. Great work. Just a couple of questions I have. One is, could you talk a bit more about the integration between the dynamic binary instrumentation and the compilation? So how do they work together?
Today, they don't work together too well. So we have the dynamic component that dynamically translates the whole thing, the instrumented binary and non-instrumented libraries. But when it sees that this is the library we didn't instrument, it actually starts inserting instrumentation. Otherwise, it is no-op binary translation pass. And today, it simply does it by whitelist. So if it sees that the name of the shared library is in the whitelist, it should instrument it. The problem is that the memory still spends quite a bit of time doing this no-op pass on the already instrumented binary. So this is a bit slow, unfortunately. Okay. The memory folks promised to fix it for us.
Okay. Another question I have is, so one of the, I guess, selling points for Valgrind is they, argue versatility or flexibility of how you can use a shadow memory. How extensible do you think your techniques are to extend, to use the shadow memory in different ways, for example, for taint tracking, in particular, if I want to have different levels of taint or different colors of taint. So I'm not interested in bit level precision, but I'm interested in the byte level granularity.
So we're very happy with the way how shadow memory works. All these three tools use more or less the same approach. Valgrind doesn't use this approach for reasons I cannot understand. They use multi-level shadow, which is very expensive. So using the same approach for tainted analysis is just obvious. It should be very simple. And I actually think that if we want to do tainted analysis, we can reuse code from MemorySanitizer by a large portion. One tricky thing about shadow memory in the way we use it in these tools, is that it uses mmap no reserve flag, so that you ask like 16 terabytes of memory from the operating system, but tell it don't reserve it for us. So the tools work on systems where there is not too much memory, but the virtual memory usage is huge. This confuses tools like ulimit-v, or if you set rlimit manually. But we don't see any other issues with the shadow memory we use. Did I answer you?
Yeah, thanks.
Thank you. Last question, probably.
So do you have any recommendations for what to do on 32-bit systems? Because like you said, it's difficult to use what you're doing on smaller address spaces. So
ThreadSanitizer works on 32-bit systems perfectly. MemorySanitizer could work, we just didn't do it. There are no significant problems with it. ThreadSanitizer is the trickiest one because it relies, first of all, it relies on atomic 64-bit loads. Well, 32-bit boxes do have atomic 64-bit loads, but I'm not sure if they're cheap. And the second problem with 32 bits is that ThreadSanitizer requires, it has 5x memory overhead. So you really could use it on 32 bits only on small tests that consume like less than a couple of hundreds of megabytes. You cannot use it on big things on 32 bits.
Sure. Okay.
Thank you for your questions. And please find me at the poster session if you have more questions or ideas.